All right, the last thing that I am going to cover that has to do with op-amps is something called PID controllers. And the reason I cover these is because it is a practical application of op-amps, because sometimes one gets asked, what kind of practical applications other than the circuits we've covered are common, and this is actually a very common use of op-amps. So every circuit that's used in a PID controller is something that you know. It is a very big combination of op-amps. It uses a lot of them, but it's just different circuits that you already have covered. So what a PID controller does is it takes a system's output that is variable, that has some kind of movement, and stabilizes it. So if you need a certain set point, say a temperature or light, velocity, vibration, those kind of things, they will take the output and then feed it through the circuit and use processes to try to eliminate the variation. And they work really, really quickly. If you have an error, it just basically takes the error and keeps processing it through multiple times until the output is stable. So they work really quickly, they work really accurately, and they're also relatively small because you can use op-amps. So how they work, and I'm not going to go into how you determine the values of K, because there is a whole process to do that, but I'm just going to kind of tell you the general way they work. There is a function R of T. That's what you want your actual output to be. That's kind of your desired point. And then what's coming out is what's actually coming out. So Y of T is what comes out of the whole process. And it gets compared to what you want. So what you want gets compared to what you got. And the difference between that is the error, E of T. And then it goes through three different things. It goes through a proportional circuit, it goes through an integrator circuit, and it goes through a derivative, I don't know why I have trouble with that word, derivation circuit. And each one of these has a particular meaning, which we'll get to in a second.
It goes through all three of them?
It goes through all three of them at once. And then all of those outputs are summed. So it's kind of like they're summed together like a summing circuit. Then that process, that output is sent through whatever it is you're doing. So the process could be a whole big circuit that does a whole lot of stuff, and then it outputs something again. So basically, the error value, again, is the difference between the two. And then the correction is applied based on the proportional, integral, and derivative terms. So there's kind of different K values you use for each one. They're weighted differently. And then the control variable is adjusted. And it's just repeated until you reach the desired set point. So which does which? So the P term is proportional to the current value of the error. So it basically just takes the error and magnifies it so that it can be seen. And it also ends up inverting it because of how the signal works. And the integral term looks at past values of the error and integrates them over time. And then the derivative estimates the future error. So by taking this error term and processing it three different ways, it's looking at the present, the future, and the past at the same time, and taking that trend and using the trend to make the error value smaller. PID controllers in general are not new. They're like 100 years old. They have been making PID controllers out of not op-amps for a long time. And this is a really old, like 100-year-old PID controller, and you can see that it actually has the derivative, integral, and proportional knobs, and the knobs are just turned to set it to different values, and then you can control processes that way. And those basically were used in processes to try to eliminate error. They're kind of big and clunky. So now that we have op-amps, they're made a little differently. So we have several circuits put together. Each one of these is actually something that you know, and how they're put together is something that you already know. So the error term comes in, and the error term is actually a negative because of how this whole process works. It's actually a negative of the error. So all the resistors that are marked R, yeah, I said why that, okay, are all equal. So all the R values are actually resistors that have equal values. So they're marked R because they're all the same value. They could all be 10 kiloohms or whatever. They're all the same.
Just the R ones.
Just the ones there are, yeah. Then RP1 and P2 are the resistors for the proportional part, and RD, RC, and CD are for the derivative, and then CI and RI are for the integrator. So all of those can be changed and be different and are made different so that the proportionalities between them are different. So at the top, you should recognize that as just an inverting op-amp circuit. That's all it is. So that's taking the negative error term that goes in, and what ends up coming out is just minus RP2 over RP1 times E of t. And so that proportional value, that the proportionality constant, is just minus RP2 over RP1. That's what determines that K value. So if you make adjustable resistors for this, you can really, really fine tune it. Or if you have a particular process that just needs standard values, you can make it that way. So that's how the first one works. Below there, this is the derivative part, or the differential, and the minus error term goes in there, and we get the derivative of it. So we take minus RD times CD times the derivative of E of t. That's exactly what we just did in the last lecture. Same exact process. The RC value there is only used to prevent the value of the gain of going too high. So that's not figured into the K value. It's only figured in as far as how the circuit's going to function in the real world. So the K value for that is minus RD/CD, and again, it can be adjusted relatively easy if the differential resistor is adjustable. That can be adjusted pretty simply. We don't adjust the capacitor. Capacitors are pretty much already hard enough to find in values, so those are usually not adjusted. The bottom one is an integrator, and this is something called actually an ideal integrator because it doesn't have a resistor in the feedback path, but it still works just the same. And the minus error term goes into that part, and we get the integral of it, minus 1 over R1C1 times the integral of the error term, and then that's the value of K for that. So each one of those basically has a resistor in that process that can be adjusted to determine the K value, which gives you the proportion of what's going to come out. Each one of these is going through an identical resistor, and that is where the summing circuit comes in. So that's where all the outputs are summed together as an inverting summer, and V out of that is just going to be minus V out from the proportional part, V out from the differential part, V out from the integrator. And you'll notice that the R values being the same means that the signal will not be increased or decreased. So each one of them is weighted equally. They just come out and they basically just all get summed together. The last stage, the only thing it does is it inverts the signal, because we made it negative again coming out and going through the summer. So the last stage is just an inverter that reinverts it and makes it positive to send it back into the process. So what does the whole process look like? Yes.
So before we jump into the math, this
Yes.
might be a little bit of a too big of a question for you to answer, but hopefully you can.
maybe.
So in control systems,
Yes.
we had a lab where we literally
Yes.
had
Yes.
a PID controller, and then
Yes.
we were tuning it to reduce the error.
Yes.
What we found was that if you changing the K values for different ones affected the error differently.
Yes.
How does each one specifically affect it?
I will show you,
Okay, cool.
sort of, in a very general way, because since I don't teach control systems, and this isn't control systems, I'm not going to tell you specifically, but I am going to tell you kind of how it works. And I'm not going to do a lot of math. I'm actually just going to take this circuit and I'm going to put it through LT Spice and let you look at each one of these signals so you can see what they look like. So we have a whole bunch of numbers, and I am not going to go through and make any calculations because you don't really need to. But we are going to look at each one of the signals, what's going in and what's coming out. And this, I'm not going to show you the LT Spice circuit. It's actually quite long and complicated because I have to have a process for it to go through. So this part is in LT Spice, and then there's a whole other circuit that's a process, and it's actually quite big, and it was a whole lot of fun. But so the error, first of all, we've got a KP value for each one, which I can give you. Notice that the integrator basically has a K value of 1, the differentiator minus 0.01, so that's really small, and then the proportional one has a large gain. So those three working together are going to be used to figure out what the error is. So the error going in, you'll notice that, first of all, it's inverted, so it spikes really low, and then it eventually stabilizes, which is what we want. We want it to stabilize, and it stabilizes within like 40 milliseconds. It's pretty much where we want it. So that's what's going in and being processed through the PID controller. So the proportional should look exactly the same, only inverted and 50 times bigger, which it does. It actually goes all the way up to 5 volts and then down. And again, you see within, a reasonably short amount of time, it stabilizes. So the proportional part is just making it bigger so that we can kind of see what the error looks like. The derivative part, we have to make the gain really, really small because the initial derivative is really big, because the gain is coming out and the signal has a very steep rise initially, which would make the derivative large. So you'll notice that the initial term of the differential goes up to like 13 volts, which is even with that very, very, very small amount of gain. So that's why the gain on that one has to be really small, because the initial error is going up and down so steeply at the beginning. So we make that small. And again, that kind of, you notice it kind of stabilizes out after a reasonable amount of time.
So if you made it big, would the voltages go even crazier?
No, it would be limited by the op amp. So the op amp can only do about 15. So if you make that too big, it'll start pegging at the top, and that'll actually affect the output, and then it will affect how the error is processed. Yes?
It looks like it has like ripples that last much longer than...
There are a few, but those get kind of balanced out by the other stuff. There's really, really, really small ripples, but yes, it's still, this is only going out to 20 milliseconds. So this one actually is stretched out because you can't see those initial things if I run it as long as the previous one. So like the error one, or the proportional, went all the way out to 100 milliseconds. So the proportional, you'll notice, still has a pretty good variation at 20. But this one is only going out to 20 because that initial ringing you can't see otherwise if it's compressed too much. And then the integral value, the last one, starts out small, and it kind of gets bigger, but it's really, 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 really tiny. You'll notice that is on the order of microvolts. And it's just an offsetting kind of thing, looking in the past and seeing what's happening. So the output combines all these together, and when it does, you notice that the signal stabilizes really, really fast by taking the combination of these three things. So my point in covering this is not to go into the details of how to tune it, but just to tell you this is what's inside it. So this is when, when you're using one of these or you encounter one, it's basically all made out of op-amp circuits that you already know how to use.